Hello everyone, thank you for coming. So today's talk will be mainly about the up vibration actually, and as a consequence I will show how to prove a pi2 of S2. So last week Peter explained how to construct the up vibration in homotopy type theory, and explain why this looks like to be the up vibration. So today I will give a slightly different construction of the up vibration and prove in homotopy type theory that the total space is actually the 3 sphere. And then this will give pi2 of S2. So just to recall the up vibration. So what we want to construct, it's a vibration over the 2 sphere with fiber S1 and total space S3. So this is what I want to construct to give another construction of the up vibration, and it will give a pi2 of S2. Okay, so I will first start with both definition and proposition. So a lot of what I will do will really look like what Peter did last week. Well, it's the same subject. So the first proposition is the following. Assume we have the following data. So we have a push-out diagram like this. Two vibrations.
Sorry, do you mean to complete the square with a push-out, or do you just mean a span like that?
I suppose I have a push-out diagram. I have a diagram like this.
You're calling such a diagram a push-out diagram?
Yes. Yes. Then I can add the push-out and yes, the input to push-out diagram.
Good.
Yes.
Just trying to understand. Okay.
Yeah. Yes, a span. Then I assume I have two vibrations over A and B. So I have my EA. So the thought is to say that this is the total space of this vibration. So I have a vibration over A, a vibration over B, and then I can pull back the vibration over A. I can pull the vibration back along F. So I get some F star of EA. And I can pull this vibration back along G. I get some G star of EB. And now I will assume that, so I get two vibration over C, and I will assume that I have an equivalence between the two. Assume I have an identification of the two vibrations, F star of EA G star of EB.
What is
Yes?
the notation you use for the pullback vibration?
F star, upper star of that. Okay, now if I have everything like that, the idea is that we will be able to construct a vibration over the push out of this diagram. So then we can construct a vibration E so this is the push out of the diagram. And I said that we can construct a vibration over this diagram, over this object, such that okay, so here I have the push out with the two canonical maps. So now we have a vibration over the push out, and I have to say that it will respect the data I have. So when you pull this vibration back along I, what you get is a vibration over A. And the condition is that this vibration is equal to the vibration EA we started with. And similarly, J star of HoTT is equal to EB. And finally, the upper square commutes. So we have a square. Commute. So there are two parts to this proposition. The first part is we can construct a vibration with these properties. And the second part is that, moreover, this diagram is actually a push-out, homotopy push-out. Okay.
Sorry,
Yes?
can I just ask, the setting we're working in, are we assuming a classical topological setting or the type theory or a more abstract setting?
Well, we are assuming a homotopy type theory, but the same kind of, well, for the proof I will use a type theory. But I guess the same statement, well, the statement is purely homotopy theoretic, so it should work in any kind of homotopy category where you have this kind of constructions.
So for instance, when you say you have a vibration over A, you say actually it's a map from A to type?
Yes.
Yeah.
Yes. For the proof, I will interpret vibration over A by a map from A to type.
And so when
Yes, but well, you can say it commute fiber-wise or it commute on the total space. It will be the same type theoretically.
And the push-outs are all homotopy push-outs?
Yes, yes,
In the sense that you defined in your previous lecture?
yes, and I will define it in the proof. So yep.
You have not been using the maps, the inclusion maps from A into, oh, you do?
Yes, yes.
Oh, okay.
I said the vibration over the push out. If I pull back along I,
okay,
I get EA.
Okay, missed the diagram. Okay, thank you.
Okay, so this proposition basically explains how to construct a vibration over a push out, a homotopy push out. It says to construct a vibration over a homotopy push out, A, C, and B, you just need to construct a vibration over A, a vibration over B, and an identification of the two resulting vibration over C. And you get the same. And if you have such a vibration, you can recover EA, EB, and this identification thanks to this diagram. And then the second part of the theorem explains, moreover, what is the total space of this vibration. So this is how I will construct the up vibration, because the up vibration will be a vibration over S2. So the first part of the proposition will tell me how to construct a vibration over S2. And the second part will tell me what is the total space. And I will use that to prove that the total space is S3. Okay, so now I will prove this proposition, and I will switch to type theory. I will interpret everything as in type theory. So first, what is the homotopy push-out? The homotopy push-out will be a higher inductive type with 3 constructors. So the homotopy push-out has a map from A, a map from B. You have first A, you have B, and for every point in C, here if you have C, you have f of C, which is a point in A. You have g of C, which is a point in B, and you will add a path between f of C and g of C. So the homotopy push-out, you have A, B, and for every point of C, a path between f of C and g of C. The map A and J are exactly the maps here, and the fact that the diagram commutes is exactly this P, basically. Now, how do we interpret vibrations? In type theory, a vibration is just a map from A to the universe. So my EA will be a map from A to type, the type of all types. And similarly, EB will be the B to type. Okay? Now, what is the pullback? This F star of EA, the pullback of EA by F, is a vibration over C. In type theory, pullback is just a substitution. So it will be the map which sends C to EA of F of C. So the idea is that the fiber of this F star of EA over some point little c is exactly the fiber of EA above f of C. And this is how you define the f star EA. It's EA composed with f, yes.
So f star EA is just a name for a function, or?
Yeah, f star EA is a dependent type over C, defined in this way.
It's the name of the dependent type.
Yes, yes. In the same way, G star of EA of EB, sorry, EB of G of C. So now I had an identification, an equivalence between f star EA and G star EB. So what is an equivalence between two fibrations? It's a fiber-wise equivalence. It's for every point in C an equivalence between the two fibers. So it will be exactly for all little c in big C. And we unfold the definition. We have an equivalence between EA of f of C and EB of G of C.
I don't see anything, sorry.
Sorry?
It's too small.
Okay. Okay, so I assume that I have this EA, this EB, and something, I can call it E of this type. These are my assumptions. And now I need to construct the fibration E. E is a fibration over the push-out. So we use the elimination rule for the push-out. It means so we need to define a map from this push-out of A and B into type. To define such a map, it's enough to define it for every point in A, for every point in B, and for every path corresponding to a point in C. So I define E on a point of the form I of A. And in this case, I will take, of course, EA of little a. Then I need to define it on a point in B. And I will take EB. And now, given a point in C, so I have a path from f of C to G of C that I call P of C. And I need to interpret E on such a path. So it should be something of type. So it should be a path from the image of the source to the image of the target. It should be a path from EA of f of C to EB of G of C. And such a path is exactly what we had here. Using the univalence axiom, this equivalence is actually a path between the two. So here it's exactly my E of C. Okay. So I constructed the vibration over the push out. Now I need to check the various properties. So what is the pullback of this vibration over I? Well, by definition, it's exactly the definition. The pullback of E over I is exactly EA. This is how we define it, basically. In the same way for the pullback of E along J, we get EB. And the last condition is also exactly the last condition. You can just check what it means. Yes?
So you get definitional equality from there.
Yes.
Will you use it later? Later you will use only the equality?
No, I think I don't use the fact that it's a definitional equality. Okay, so now what we want to prove is that to understand the total space of that vibration, and to show that the total space of the vibration is actually a push out of the total space of EA and EB. So we want to understand the total space of E. So to understand the total space of E, this is actually a special case of a general schema. I call the flattening lemma, which says roughly the following. If you have I, a higher inductive type, and if you have a dependent type over I defined by the elimination rule of I, defined by induction on I. So we are in this situation because we have I is the push out of A and B, so it's a higher inductive type, and we define a dependent type by the elimination rule. Then the total space of P can be seen as some kind of flattened higher inductive type. I'm not very precise, but I will explain what it means in this situation. In the situation here, what we have is that we have this push out of A and B, and we have a vibration over A, a vibration over B, and something in between corresponding to the path in C. So what it means, for instance, that is if I have a point little a here, above little a, there is a whole type, which is the fiber over this little a. Similarly, for every point, there are whole types, and so on. And for every path in the base, we have an equivalence between two such types. And we can actually see the total space as a higher inductive type by itself. Instead of having for every point of A some sort of big point corresponding to the fiber, you can just consider all the points in EA of A individually. So what it means is the following. The total space of the fibration E can be seen as the following higher inductive type. I have some I tot, which will correspond to A, which says for every little a in big A, and for every x in EA of A, then I have a point in E tot. For every A and for every x in the fiber, I have a point in the total space. Similarly for J. And then for the path, what I want to say is that for every point in C, so for every generating path between A and B, I will have a collection of paths between the two fibers over F of C and G of C. I will have some P tot, which is for every point in C, and for every Z in the fiber over the correct point, so it will be EA of F of C. Then I have a path between the corresponding points. So it will be between E tot, FC, and Z. And J tot, G of C, and my equivalent that I had here, EC of Z.
You said E tot, but it was I tot.
Yes, I tot, sorry. Yes. So for every C, it corresponds to one generating pass of the push-out. One generating pass of the push-out corresponds to an equivalent between EA of F of C and EB of G of C. So instead of having an equivalent between the two types, I said that for every Z in EA of F of C, I have a pass in the total space from this particular point and its image by the equivalence. And now if you look at this definition, this is exactly a map from the total space of EA. This is a map from the total space of EB. And this is exactly an equivalence corresponding to this diagram.
So this flattening lemma is not something that you can express, but you use an instance of it for your
Yes. Yes, it's a general schema for
lemma.
Yes. For every higher inductive type, you have a corresponding. Yeah.
Is this different from the reduction of 2 hits to 1 hit?
Yes, it's different.
It's different.
Yes.
It's similar. Why do you call it flattening?
Because the total space looks like a collection of blobs of types, and here I consider every point at the same level, every point in every fiber at the same level. It's looks like some kind of flattening. I don't know.
So logically, you've flattened two definitions into one. It's not a geometric flattening, but it's a logical flattening.
Yeah.
The motivating example was the universal cover of the circle, where it is a geometric flattening, right? When the universal cover of the circle is defined as a dependent type, it looks like a helix, and this flattens it out into a straight line.
Okay.
For the corresponding version for that.
So it's a bit like, if I understand what you just said, like constructing the universal cover from, or maybe the total space of vibration from the functor.
Yeah,
Something like that.
It's a group they consider.
It's the category of elements. Or
It's like the category of elements.
Yes. Yeah.
Exactly that, yeah. It would be nice to have a sort of terminology. It's a bit, I mean, I think some people, or maybe people call it the total space like an integral sign.
Yeah.
Taking a total thing, it's like integration,
Yeah.
which I like very much.
Yes.
I'm not sure I like the flattening terminology, but it could be maybe because it's a logical origin or something. Yeah.
Is it because you're losing some structure in some sense? You deduce the structure in the total space?
Yes. In the fibration, you have the structure that it's a fibration over the push out. Here we're just describing the total space without the map to the push out. Without the.
Would you translate this into French as étalé?
I don't know.
Translate the French. If the French would be étalé.
I haven't tried to translate it to French.
No, but you say that because you want to connect it with some other use of the word étalé?
Yeah. All the time to change type of thing when you take the étalé spaces with
Yeah.
It definitely is.
You've stated it, and we always have, you've used it in the past for the case where I is high inductive and P is defined by the induction property pi. But in general, isn't there a corresponding higher inductive type that can be made for a type I and a family of types P over I? Could we make such a total space construction?
If I is not a high inductive type,
Yeah.
well, I don't know how you would describe the total space. Here the structure of the total space is really the same as the structure of the high inductive type I.
Yeah, determined by the
Yes.
inductive property of I.
So, I have another question that may sound stupid, but E is an equivalence between a subpart of A and a subpart of E. It's the equivalence that was used between F star of EA.
It's not a subpart of A and subpart of B. It's between some fibers of the fibration EA and some fibers of the fibration EB. Yes?
So maybe a different way to look at this lemma could be as a sort of a generalization of what you're saying here about that diagram being a push-out. That generally, if you have a base that has some left universal property, and then you make some fibration over it, which is described via that left universal property by what it does on pullbacks to the inclusions, then the total space will also have a left universal property analogous to the one of the base space, but described using what it was over the fibers of the inclusion.
Is it
Higher
not
total
what
space
Charles
is
Rex
descent.
called patching, the patching property of patching? Is it that I have a hard time remembering exactly what is this terminology, but is it patching or this gluing property?
I think descent is
Patching.
Descent.
What did you say, Eric?
I said descent, but descent.
It looks like descent.
Yeah, but since this is homotopy descent, but maybe descent is good too, because after all, let's call it descent, although it's homotopy descent. I think that maybe Charles Rex had this different word because it was homotopy descent. But now we are taking over, and let's use descent for homotopy descent. Yeah.
And I think descent descent is the opposite. Descent is you take the co-limit and then you figure out that all the inclusions were really pullbacks. Here you are taking the pullbacks and you figure out that it's really a co-limit. I think it's more
Yeah,
the,
right.
it's more the locally Cartesian
You
closed.
already have this co-limit and you put it, yeah.
Think of it all as being descent. Classical maps as descent.
If we think of the co-limit as some kind of integration process, we take the total something, right? This is like the inverse of the integration process. I don't know if we should be called it differentiation, but
In a way, it's kind of, if you think of it as integration, this is kind of like a Fubini theorem.
Fubini?
Yeah, because like you're integrating, taking the
Yeah.
total space over a space which is itself a colimit.
Yeah.
Which is like a total space, so it's like
So
reassociating.
you put it together out of the
Yes, we can call it Fubini.
Yeah. Is there a theorem in topology saying that if you have a fibrations over a CW complex, and if the fibers are, I don't know, CW complexes, then the total space is a CW complex or something? As a CW complex?
I think there may be a theorem of something like that, which refers to homotopy types of CW complexes.
There's certainly at least that for fiber bundles. That's a well-known theorem for fiber bundles. Whether it holds for general fibrations, I'm not sure.
The problem is a co-limit of fibrations might not be a fibration.
Yeah.
So this is where we're taking the approach here of defining it as a fibration and then comparing the total space with the colimit as a homotopy colimit.
Okay, so we can show that this is indeed the total space of the fibration, and this is also a representation of the push-out, which proved that the diagram here was a push-out. So now I will explain how to use that to construct the hop fibration, and actually I will do something a bit more general, because a lot of what I will do only use the fact that the circle is an H space, so I will do it in general. So I will first define what is an H space. An H space
H refers to
Heinz up. It's a pointed space A together with a multiplication operation, a map from A times A to A. Such that the multiplication by the base point is homotopic to the identity. So the two maps mu E something and mu something E. So there are two maps from A to A. Are homotopic to the identity map of A. So for instance, if you take, well, in topology, if you take any topological group, then it's an H space for the multiplication, because multiplication with the with the identity element give the identity function. But they are, it's much more general. You don't assume associativity or inverse or anything like that.
So is mu part of the structure or not?
Yes, yes. The space is the pointed space, the mu, the multiplication, and the homotopies to the identity.
Are the homotopies based homotopies?
I don't think it's needed. We'll see. Yes, and for instance,
Wikipedia says that the homotopies are sometimes based.
yeah. Okay, so I don't think I need the homotopy to be based.
The definition is already there. The H space.
Yeah, it's a classical
Yeah.
notion of algebraic topology.
For instance, the circle, I will prove later that it needs an H space, but the example you have to keep in mind, in topology, it's just a topological group. So you have a multiplication operation, and it gives the structure of H space. And this is with the circle that we will get the up fibration.
Excuse me, I didn't follow.
Yep.
What is the multiplication here?
For S1?
Yeah.
You can see the circle as the unit complex numbers, and you have a multiplication.
Okay.
Or you can see S1 as the real number modulo 1, and you have addition. It's the same. It's a group. Okay, now assume A is a connected H space. I don't know if they are usually assumed to be connected. Well, I need it to be connected anyway. So assume A is a connected H space. Then for every x in A, the map multiplication by x are equivalences.
What is the
Okay.
equivalent of this in type theory?
This is type theory.
Connected.
Connected, sorry. Connected mean that the zero truncation of A is contractible. You need truncation or something like that to define connected.
You can do it without any higher order types by just saying it's orthogonal to fibrations of H sets.
Okay, yes. Okay, thank you. So the multiplication by any point is a homotopy equivalent. So intuitively, this is very easy because yes. Another way to define connected is to say every point is connected to the base point, but connected in with a path which does not have to depend continuously of the point somehow. It's a -1 truncation if you want. So the proof, at least intuitively, is just every point x is connected to the base point by a path. A is connected, so every point is connected to the base point. And the multiplication by x is homotopic to the multiplication by the base point. But the multiplication by the base point is supposed to be homotopic to the identity function, so it's an homotopy equivalence. So for every x, multiplication by x is an equivalence. And in the same way for multiplication to the right by x. Okay?
And we're allowed to do this because it's connected by a path in the sense of the -1 truncation of paths, and being an equivalence is a -1
Yes.
truncated thing, so we can prove that by reasoning out this -1 truncation.
Yes. So here we get a proof that this is an equivalence given a path from x to e, but this proof cannot depend in any way of the path we choose, because being an equivalence is a proposition. So it cannot depend in any way. So it's enough to have that the -1 truncation of the type of path between x and e is inhabited. And this is exactly what connected means, basically. Okay? So now I will use the lemma. Okay, first I will define the suspension. So if you have a space A, the suspension of A, S of A, is by definition this push out. You have 2 points, and you have a many paths between the 2 points, if you want. Okay, now we will define a vibration over the suspension of A. Okay, sorry, assume A is a connected H space. We will define a vibration over SA with fiber A. And in particular, for the case where A is S1, we will get a vibration over S2 with fiber S1, which will turn out to be the up vibration. But we can define this vibration more generally for any H space A. So the first lemma I proved explained how to define a vibration over SA, because SA is a push out. So we have SA here, of a push out like that. And the lemma says that in order to define a vibration over SA, you need to define a vibration over 1, another vibration over 1, and an identification of the 2 vibration over A. So the vibration over 1 is just a type, and it will be the fiber. So I will just take the space A. Similarly here, I just take A. Then when I pull back A along A like that, I get the product. And here I get the product too. So now I just need to find an identification of this A times A and A times A over A. So this map E should be an equivalence of A times A to A times A, which commutes with the first projection. So I will define it in the following way. I send xy to the pair x because it has to be x because it commutes with the first projection. And the second element will be the multiplication mu of xy. So this is an equivalence. Because we can express its inverse. We have the e minus 1 a times a to a times a, which sends uv. So if you start with x and x times y, to recover x and y, you first get the first element, u, and then you need to multiply by the inverse of x if you want. So take the multiplication by u inverse. This is an equivalence by what we proved here, and apply it to v. Yes?
So when you did the lemma general, you described E slightly differently, not as just an equivalence of total spaces, but as a fiber-wise equivalence. And so looked at as a fiber-wise equivalence, then for each A you're giving an equivalence from A to A, and there it's even clearer from what you just said that it's an equivalence on each fiber.
Yes, yes, indeed. Yes, you can see just an equivalence on each fiber, and we take for the fiber over u, you take the equivalence mu by u. Yes, thank you. It's simpler. Okay, so this is an equivalence. So I can apply my lemma, and I get a fibration over SA with fiber A by construction. And with total space, which is described by a push out. So the total space will be the push out of the top diagram. So you have A, and A times A. The first map is the second projection, and the second map is the multiplication of the space, of the H space A.
There is a small point. In your diagram, the little triangles where
Yeah.
E is.
Yes.
Called E or L? I don't know.
E.
E, okay. This should be commutative, no?
Yes. Yes.
What are the maps, the projections?
The first projection.
And the second? Oh, both.
Both the first projection, yes. The second projection are the two maps here.
Okay.
If you want, I can call
Okay,
the fiber AF.
that's fine. It's just because. Yeah.
What's confusing, the fiber and the base are the same. So. But one of the two A is the fiber that we pull back along this map, and the other is the base. So both are the third projection.
I think this is actually clearer in the type theory view rather than thinking about the total spaces at all. These are right. So these are families, type families, which are just over A. We have the constant type family, which takes everything to type A. And then just having a fiber-wise equivalence of that. So for every A, we have equivalence from A to A.
I guess it's okay.
So they are both constant families of type. The base is A, and the value to every point is again A. And this is for every little u in A, an equivalence between the fibers. For every u in A, you want an equivalence between A and A, which will be multiplication by u.
Yeah, I'm a little bit confused for maybe for a very stupid reason. It's just because when I write A cross B, 2 on the other side. And it seems that you're sort of cheating a little bit here by putting pi1 on the right-hand side and on this side, and pi1 on the left side on this side. So, of course, you could rewrite this by putting pi1 and pi2 and using the symmetry isomorphism.
Or just by drawing the diagram with both sides facing left to right.
Yeah. Yeah, so probably that I am just over formal here.
But this comes from I upper star and J upper star. And you should define upper stars in some uniform way.
Okay.
Yeah, they are both pullback of the constant vibration.
Yeah, of the same map.
Yes.
Actually. So
Along the same.
yeah.
It's the same object twice.
Pi1 is going to the left factor of the product in each case. It's just that on the left half of the diagram, the product is drawn with its left factor going down to the right and
Okay.
even formally, the symmetry doesn't need to get used. It's just in how we project it onto the blackboard.
The two squares, the two upper squares are actually the same. It's the same square twice.
Yes.
Okay.
Depends what you mean by same.
Yeah, but I hope that this convention will be the same as the general one, where you explain, you know, how to glue, I don't know, push out, etc. As long as it's a special case of the general convention, I would say it's okay.
Yeah, it's not the diagram of a product. It's a diagram of a pullback of a vibration along a map.
Yeah.
It's not symmetric.
Okay. So
In this case, it happens to be a product.
okay.
Can you re-explain what you said about the total space?
So the first lemma I proved was that the total space, so when I define a vibration in this way, the total space is a push out of the top diagram, the diagram with A cross A, and A. So this is just what I'm saying here. I have A cross A, and A. The pi2 is the map here from this A cross A to A. And then the multiplication is just composing the equivalence E with the other map. Okay, so now this is still not very useful because this mu is a bit strange. We don't want a mu in here. But actually, it will. We can get rid of the mu and replace it with a pi1. The idea is that so this is the span defining the total space here. And what I'm saying is that it's equivalent to the same span, but with pi1 and pi2 instead of mu and pi2. The two diagrams are actually equivalent as diagram. So how do you prove that two diagrams are equivalent? You need 3 maps and a commutation for the 2 squares. So a map from A to A, take the identity on A. Here I take the identity on A. And this map F should be a map from A times A to A times A. And should make the 2 square commute. So it's not difficult to understand what is F, because if you take F and then pi1, you get mu. So F of xy will be first mu of xy. And then if you take F pi2, you get pi2. So F of xy is mu xy y. And now the identity function are 2 equivalences, and this map F is again an equivalence. for the same reason, basically, because you can define the inverse map. We'll send uv to, so the second component will still be v, and the first component, now you need to take the inverse operation of multiplying to the right by this y. It will be some mu something v minus 1 of u.
This is why you need the invertibility on the two
Yes.
sides, so to speak.
Yes, so I need both one to be able to construct this diagram, and the other one to prove that the diagram is pi1, pi2 diagram.
This is really sort of strange in the sense that you're constructing this fabulation using mu, and then you show that it can be constructed without it.
I don't show that it can be constructed. Well, the total space can be constructed without mu.
So somehow
Yes.
that is,
Yeah.
it's kind of strange.
Yeah.
If one looked at the total space constructed without mu, then to recover the map from the total space down to the suspension, mu would come back in. And so to get the data of the total space together with its map to the suspension, one needs mu. But we can, and if one defines it as a vibration, then the mu goes into it. But if one just wants the total space alone, then one can get the mu out.
Okay, so the total space can be constructed without mu, but the map itself is using mu. Okay. Wow.
Then obviously, when two span are equivalent, then the push-outs are equivalent. Yes. We use the invertibility of mu. It's the lemma above. The two mu something by x is an equivalence for all x. So we just define the join. If you have two types A and B, two space A and B, you define the join of A and B, written A star B, to be the push out of A and B along the product with pi1, with the map pi1 and pi2. So what we proved is the following. If you have a connected H space, then there is a vibration over the suspension of A of fiber A. This is what we constructed, and of total space, the join of A with itself. The push out of the bottom line is exactly the join of A with itself.
Is this a classical theorem?
Yeah. This is called the Hopf construction on that map.
Oh, really? It's a classical theorem.
Yes.
Have you seen the statement?
No.
Wow.
I just noted the construction, that most of the construction only use the fact that S1 is an H space.
Okay.
So
But H is for up, I suppose?
Sorry?
H is for up.
also get this kind of arrive at the definition of an H space by looking at this construction of the thing as a
Exactly
suspended
what you need to make the three
Yeah,
compounds.
he introduces H space because there may be.
Yeah, and it's not associative because the higher compounds aren't associative. It's like the minimal hypothesis.
Does the classical case require H to be connected? Or A to be connected?
Yeah.
Probably, yes.
Yes.
Because I'm really using it to prove that multiplication by any x is an equivalence,
Yeah.
just because x is has a path to the base point. If A is not connected,
Okay, okay. Of course,
won't get.
you add this hypothesis in without supposing.
Yes, you can just assume that multiplication by any x is an equivalence. Is that what you mean?
So, for example, you could have a discrete group or something.
Yes, yeah. Okay.
Yeah, that's a theorem.
So now we will construct the up fibration. So the up fibration will be the special case where A is a circle. So I first need to prove that the circle is an H space. Or to construct a structure of H space on S1. So I need a map from S1 times S1 to S1. I can purify, and it's the same thing as a map from S1 to the map from S1 to S1. And now I will define such a map by induction on S1. So I recall S1 is defined with one base point and one loop. We have 1 point and one loop, like that. And I want to define a map from S1 to the space of maps from S1 to S1. So I first need to explain what happens for the base point. What is the map corresponding to multiplication by the base point? And multiplication by the base point will exactly be the identity function. Because we want S1 to be an H space, we want in particular this function to be homotopic to the identity function. So we take the identity function. And now for the loop. So we have the identity function, and basically what we want here is an homotopy between the identity function and the identity function. So you have the circle, you have the identity function, and you want an homotopy from the identity to the identity. So this is exactly what Peter did last week. Of course, that you could take the trivial homotopy, but in this case, it would not be a structure of H space because multiplication to the right by the base point would be a constant function, and the constant function is not homotopic to the identity. So we cannot take the trivial homotopy. But what is the type of all homotopies between the identity function and the identity function? Using function extensionality is just for every x in S1, we want a path from x to x. Homotopy, for every x, you choose a path from x to x. So we want some map H which has the following type. And again, this is a map from, this is a section, well, this is a map, a dependent map whose domain is S1. So I will define it by induction on S1.
This is each time I look at this, I can't believe it.
So we need to explain what happens for the base point. For the base point is when you take the homotopy from the identity to the identity and you specialize it to the base point, you get a path from the base point to the base point. And so we need to choose a path from the base point to the base point. And we will take the generating path loop in order to have the homotopy which does exactly one turn in the right direction. And now we need to explain what happens for the loop. And for the loop, basically, you have to say you have this dependent type for every point in the circle, the type of path between x and x. You have a special element at the base point, which is the loop, and you need to say that when you transport this loop in this vibration along loop, you get the loop. So, okay, I will not do the explicit calculation because, well, you will not understand. You have to do it yourself to understand it. It's just the dependent elimination rule of the circle. It's very easy, but you need to do it yourself to understand, I think. It's
not that hard to describe.
Yeah.
Because the transport of that dependent type around that circle is post-composition.
Yes, it's a composition. Yeah. So what you get is you need to prove that loop composed with loop composed with loop inverse is equal to loop. And this follows from the elimination rule and for all kind of different computation rule and so on. And this is true. You can just remove loop and loop inverse, and you get something in this type.
Yep.
So you get this this multiplication.
Can someone explain it to me in terms of just standard homotopy theory? Or describe it. Suppose that you want to describe this proof or this construction of the multiplication to some dumb homotopy theorists who do not understand homotopy type theory. What would you do? I mean, because it should be possible to explain that in terms of.
If you unwind the formulas, it's just the map corresponding to mu, which is multiplication on the circle, applied to, you take an adjoint of it.
No,
it really is that map. I mean,
no, but yeah, it's
just
about
that-
this
but
map, but it's about actually defining or constructing this map.
it's just that, in a sense, it's just that we're doing it in a coordinate-free way, if you will.
No.
But I think it's not maybe answer the question a different way. This is, we're looking, so in H, we're looking at the vibration over the circle of loops in the circle.
Yes.
So the vibration of a point is loops in that point
Yeah.
itself. And we're trying to construct a section of that
Yeah.
vibration.
Yeah.
Generally to make a section of a vibration over the circle, we want a section. We need a point over the base point of the circle. So over the base point of the circle, we choose the single loop once
Okay.
of it. And then we also need to say that when one transports that point around the loop once, the result, one then needs to give a path from that to the original point. And now one looks at how transport acts in the loop vibration, which comes from how transport acts in a path vibration, which is that if in the path vibration, one takes a path and then transports that in a path in either point, either endpoint of the base, and that gives either pre or post composition. So when one does that with the loop vibration, it becomes conjugation. So in any space, if I have a loop in the top and I transport that along a path in the base to get a loop at the other point, it's conjugation. It's the very traditional way of, if you've got 2 points connected by a path, how you turn a loop in one into the loop at the other.
Here's a more topological way of saying that, maybe.
Can I say one more line and then? So what we exactly have to show is that when we take the loop and conjugate it by the loop, we get back the loop, or we get something with a fast loop, and so that's exactly the send type that we're after.
Yep.
So then, Mike.
So a little more topologically, we have vibration over the circle whose fiber over a point is the space of loops based at that point. And so we define a section of that by sending each point to the loop which starts at that point and goes around it. And goes around the circle and back to that point. And that's a continuous section because as the point moves, then like the loop rotates.
Yeah.
So that gives us, assigns to every point on the circle a loop in the circle, which is exactly the.
But the way that we get that out of the higher eliminator is because as one follows that loop rotating around, what one's getting to each point is the same loop conjugated by the path from the circle. And so we end up with the loop being conjugated by the whole loop. But that is just the original loop we started off with, so we're good.
Yeah, I do not want to interrupt.
Carry on.
Thank you. I need to put this in my file.
So you know the type here that you're expecting?
Yes. Here the dependent elimination rule gives you some type. You can apply some computation rules and you get that.
And are we allowed to use ID now for this hole?
Not ID. Well, you're allowed to use anything that proves this equality.
And this is an equality in the sense of.
This is
You don't use definitional properties of.
you will use the fact that a path composed with its inverse is the reflexivity path, and that composition with the reflexivity path is the original path.
But these are all propositional.
These are
Yeah.
propositional
Yes,
equalities.
everything is propositional. Here, you just need any kind of propositional equality. Well, any propositional equality doesn't matter. So we defined the multiplication, but now we need to prove that it's indeed an H space. We need to prove that first, multiplication by the base point is homotopic to the identity, but multiplication by the base point to the left was defined to be the identity of S1, so of course it's homotopic to the identity. But we need also to prove that multiplication to the right by the base point is homotopic to the identity. So what does that mean? That means for all x in S1, mu x base equals x by function extensionality. So again, we'll use the dependent elimination on the circle. For the base point, you have the multiplication of base and base, which should be equal to base. But this is the case by definition, because we have base on the left. So we get multiplication base equals base. And when x equals loop, well, you can just unfold the definition. And what you get is exactly proving that what you have put here is equal to loop, which is the case. Because this h, basically this h is multiply loop by something. And this case is multiply loop by base, and you get loop. This is exactly what you need here. Multiply loop by base, and you get loop. So now we have an H-space structure on S1.
So when you mean x equal loop,
Yes, I mean.
Well, for the other case, yeah.
So you send base to ID. I don't see this. You send base to ID and you send loop to prove that.
I said yes, and I said loop to prove that it works, and you can unfold the definition, and you will get you need some kind of loop equals loop, and you can prove it. But there are a lot of computation rules that are not computation rules, so it's a bit complicated to do. But okay. Now I define the two-sphere S2 to be the suspension of S1, S3 to be the suspension of S2, and if I apply the lemma about vibration over suspension of H space, what I get is that.
You're applying the theorem now.
Yes, yes. For A equals S1, what I get is a vibration over S2 with fiber S1 and with total space the join S1 join S1. So we're not done yet. We need to prove that the join of S1 as S1 is indeed S3. This is what we want to prove. And to do it, I will use a very nice trick that I learned from Eric. And I will prove something more general, is that the join of any space A with a circle is actually the double suspension on A. Join is the A join B as the push out of A and B along the product. So basically you take A, you take B, and for every point in A and every point in B you add a path. You have a whole bunch of paths. And the way to prove this proposition, that I will draw a two-dimensional diagram, and I will compute colimits in one direction and then in the other direction, and on the one hand I will get the join, and on the other hand I will get the double suspension. So let's consider the following diagram. There are a lot of different ways to see that, but I think they all use some kind of argument like that in the end. Okay, so I consider this 3x3 diagram. So the maps here are the co-diagonal. The map here sends the first element on the first element here, and the element in the second component in the second point here. So this is a commutative diagram. And now I can compute the colimit of each of the line, and then the colimit of the resulting column. Or I can do it in the other direction, compute the colimit of the columns, and then the colimit of the lines. Okay. We'll redraw it here. It's the same diagram, I just want to have some space below. So what is the limit of the first line? You have A A, and for every point in A, you add the path. So you get some kind of cylinder on A. The colimit here is exactly A. What if the colimit of the bottom line? You have 1 point, one other point, and 2 paths between the 2 points. So what you get is a circle. And what is the colimit of the middle line? You have A, and then A plus A, and all the paths like that. So what you get is exactly S1 times A. And the two maps that you get are exactly the first projection and second projection. So now when you compute the colimit of this column, you get exactly, by definition, S1 join A. Okay, now, what is the colimit of the first row? You have A, then you have a point, and for every element of A, you have a path from A to this point. So it's a cone on A, so it's contractible. It's just a point. The last column is exactly the same, just a point. And the middle columns, so you have, on the bottom you have 2 points. On the top you have A. And in between you have A plus A, and you have something like that, basically. So this is a suspension of A.
If we were really going to prove this, we would use the flattening lemma to show that each of these comes out to be the same higher inductive type.
No. To prove what, for instance, that this is the suspension?
For example.
We can do it with the same kind of lemma. You have something like 1, 1, and I don't remember, something like that. And or you can just define the two maps. And you can just define the map back and forth and prove that they are inverse to each other. It should not be hard.
Okay.
And now when you do the colimit of the line, you get the double suspension on A. And the two are equivalent because they are both basically the colimit of this two-dimensional diagram.
This is like homotopy version of double counting in combinatorics. Where you double count, you count things in 2 ways in a bipartite graph.
Yeah.
It's also another for B.
Okay, so in particular, if you take A equals in particular for A equals S1, what you get is S1 join S1 is the double suspension of S1, which is by definition S3.